All right, I see it live on YouTube.
Oh, you have password to the Gmail the YouTube channel. Welcome to our professional start. As always, we're talking about password as we start streaming. Welcome.
Anyways, our password is.
I am going to. And Jared, you were just getting ready to tell us what street you grew up on as a child.
Yeah.
Mother's maiden name.
First
Social security number.
Yeah, first pet, very important.
So, welcome everybody to Space Force Theater 5000. We are once again live on the YouTubes, and we were crazily decided to do shows every 2 weeks while we were closed to the public, because the other show we do at our day job, All Space Considered, was taking a little bit of a hiatus. Well, out of the blue, after we had planned this show, after I had arranged to have our guests join us that we'll introduce here in just a minute, the other show said, we're happening. So we have that one tomorrow night. And I actually urge you all, if any of you are watching it, to tune in to All Space Considered Remote on YouTube live tomorrow night at 7:30. But tonight, I'm so happy to have you here with us and our guest, Dr. Eloise Devance. Did I say that correct at all? I probably butchered.
Yes, it's good. It's all good.
Okay. And now you, despite the fact that I know you grew up in France and you went to school in England. What school, where did you go to school?
So if we're talking about school, I went to school in France. I moved to the UK for university, and I went to the University of Sheffield.
Oh, yeah, University of Sheffield. Yeah, here we interchange school and university. It's colloquial for California.
I'm not up with the cool American lingo, so you'll have to keep me up to date.
Our cool slang.
Yeah, our butchering of a fine language, you mean. So anyway, but yet you're not joining us from the continent of Europe. That's what the point I was trying to get to today, because you're currently a researcher in New Zealand.
I am, yes. New Zealand, Aotearoa. And it's a pretty good place to be in the world right now.
I was going to say that.
Yeah, right?
You know, I do want to talk a little bit about a few things that are going on in the world right now. But first off, what are you going to talk about tonight? Give folks a little peek into what you're going to say, and then we'll get back to you probably in about 20 minutes, and we'll hear more from it. But what is your topic for us tonight?
Okay, so today I'm going to be telling you about stellar deaths and cosmic explosions and the origins of life, or rather the elements and the little Lego bricks that are really necessary to make life on Earth and where they're made in space.
Well, that'd be fun. That's always an awesome topic. In fact, anyway, can't wait to talk about that. That's going to be exciting. So folks out on YouTube, listen in. We'll be taking questions live during the show directly, so you'll be able to type them in. We'll all kind of try and keep an eye on that as we can. But tonight, I did want to open the show talking a little bit about the conditions on Earth and the global pandemic that we are experiencing. And it's just, I have to say, it's so disappointing to see folks like, Elon Musk and frankly, the bullshit that he's speaking about right now. And you know that it's connected to that nearly $750 million bonus he's about ready to get if his company, maintains its stock level or whatever it is. I'm not so up on how all that financial stuff works, but it seems like that would make sense why he would want to not have his stock tank. But anyway, it's just disappointing because we need to listen to the scientists. And when the scientists say it is safe to reopen, then we can. And in my opinion, we need to have more tests. We need to have more tracing. Here in LA, you can finally go get a test if you want one. You don't have to have symptoms, nothing. You can just go get a test. So if you think you've been exposed, go get a test. We have enough of them, and it's important for people to be doing this. And once we have enough tests, we then can trace. And if you trace, then you know where the virus is, and you have a better chance of saying, oh, it's in... I don't know if it's in West Covina, so sorry, West Covina. But if it's in West Covina, you don't go to West Covina. So anyway, so just a little rant about that. And it's disappointing to see folks with power and money and so many followers cherry pick data, cherry pick things that are happening. And it's sad. Yeah. I don't know. What does everybody else think about that?
I am happy to see that most of the people that I follow have mostly been calling him out on that kind of thing. Yeah. Which is a little refreshing. That's all I got.
Yeah. I had to talk with my brother the other day, and there is some counter argument to opening up a bit. The UN is actually kind of shedding light on that a bit as well. Since so few people are working, there's a mess of food that's rotting instead of being distributed. They're expecting a huge food productivity shortfall, which means massive famine for the countries that are not big producers. If they're mostly importers, they're kind of effed in the B real soon. So there is some argument to be made for it, but you got to do it safely. And these people with machine guns on the steps of Michigan, that's not right. Yeah.
Anyways, welcome to our politics show.
Yeah,
this is
welcome to the show.
Well, no, but Elon Musk is someone that he drives space conversation in this nation right now. And what he's done with his rockets is simply amazing. And that's why I wish he would stick to rockets. And the Tesla, I know people that, I don't know, I was hoping to get one. Instead, I went with the Kia because I could afford it and drive me to Reno, it being the plug-in hybrid. But nonetheless, I was looking into it, and he's done remarkable things with rocketry. As a kid growing up, thinking and seeing those old videos of rockets landing and thinking, well, maybe one day we'll do that. He did that. Yeah. He's the guy that made it happen. Now, we did vertical takeoff and landing with other rockets in the past, but nobody
DCX.
What was that, Jared? What was it?
DCX, baby. 1992. So
pictures or didn't happen.
Yeah,
just saying.
So it has.
Blue Origin snatched up all those engineers. Let me tell you. So.
Yeah, no, and rightfully so. And Blue Origin is doing stuff right now too. In fact, I love the fact they're looking to upgrade into something that's orbital. But that's what SpaceX did. Is they did a booster that can take payload into orbit, and then decided to reuse the first stage of that. And that's the part that's remarkable. I just wish he would stop. Let the folks that are experts on virus handle that.
I mean, I don't mean to rain on your parade, but it's not the first time that Elon Musk is only listening to his own science. Because I've had people for a few months to a year now with his Starlink that is ruining the sky, and he didn't consult any of us.
Yes,
thank you very much. And you get armies of Musk bros in our Twitter threads about Starlink, and it's startling, you know. Yeah.
Oh, I've engaged with them as well. It's not a habit of mine, but it's a failing of mine, perhaps.
Don't.
No, it's not worth it. I've learned that.
And beat you with experience.
And last night I've learned a new hobby of mine: make a minor mathematical error in a point you're making, and then the trolls will do nothing but focus on that, despite the fact it doesn't have any bearing on the point you're making. So yeah, that'll teach me to make points late at night. But I don't know. It's I did see another interesting tweet, and I'm going to open up a can of worms just because whatever. Like I said, if we're going to burn some bridges, we may as well get rid of the people we don't want fans of the show anyway. You shared a remarkable lecture, and I thought it was very cool because growing up, of course, being interested in physics, you get given those Feynman books, and so much of them are charming and interesting. And there's, you know, he tries to be this likable character, and that's really what he is. It's a character he's dreamt up. But then you see these little snippets that are so darn disturbing. And as a youth reading it, you don't get it. But then you go off to graduate school and you see how your female friends are treated, and you see how women you respect are treated, and you see how women that get where they're going, what they had to go through, and you hear these things and whatever, and then you think back to those Feynman books and the horrible precedent that they set and how difficult it creates the landscape for women based on just those books. I wanted to swear there a little strong, but Mom, are you watching tonight? Anyway,
if she was watching, you would start swearing.
I thought it was a very cool video because this actually came up recently, and at our other job, I'm not supposed to talk about it too much, but we rejected the notion of using some Feynman stuff and using him as an example. And our boss agreed with that. Obviously, she's pretty cool that way. So it's nice to see the landscape changing on all of that, and just, you know, be able to talk truth and still respect the physics that the man did, but understand that he wasn't this groovy dude that you want to be like. You know?
That was Sagan.
Carl Sagan is our only hope. He's our Lord and Savior. He's not been pushed by any of that drama yet, and I will hold on to this for as long as I possibly can.
Yeah. Yeah, well,
the
Fred
Mr.
Rogers.
Rogers of astrophysics.
Carl Sagan or Bill Nye. Just you suddenly. I will.
No, you need to let Bill Nye go, perhaps.
Yeah, there was something.
Oh.
Oh no.
Oh God.
See, Bill Nye struck again. Anyway.
But Bill Nye's watching. Bill Nye is always watching.
No, I have to say, Bill, I will say this to be somewhat political. Bill, he controls a fair amount of respect around a lot of people because his image and his show was crafted to do that. And I have to say, I credit the producers.
You mean the Beastman's World knockoff?
Well, but even still, if you want to argue about that one.
Ouch! Oh, ow, 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 ow.
I was wanting to say that for so long.
Have you? Okay. But still, nonetheless, he introduced a lot of people to science, and he did it in a way that was overall good and correct and healthy. But there are times that Bill has become a little bit about Bill, in my opinion. But maybe Bill will come on this show, and we can talk to you about this, Bella. No, I'd love to. I do want to go visit Planetary Society at some point, which brings up our next point. Let me check the time here. I don't want to get too far behind. No, we're doing great.
Yeah.
But you were just about to announce the Space Force roast of Bill Nye, starring Bill Nye.
Yeah,
Roast of Bill Nye. No, we've got other targets. We could roast Bill tonight if we wanted to. One of our colleagues that bowed out. Anyway, we won't do that tonight, Bill. If you're watching. Anybody checking the YouTube chat? Is he typing in right now?
It's literally just me and Sarah.
Yep. Because people went to that other link. That one had 5 viewers. I posted the new link to Facebook, but
did you
maybe a minute.
You need to post into the chat of that other video if it ever goes up.
All right.
If you could do that, that would be. Keep an eye on that as I blabber on here for another
Twitter,
moment.
I'll retweet it.
I did tweet and added you.
I retweeted something.
Yeah, if it was most recent, then that at least was the link to the main page, and they should be able to see what's live. It should show them the live.
I'll check my notifications. I thought it would be rude to be on my phone during a podcast, so I've not checked. Oh
gosh, this sort of a podcast though? Heck no, this is our style. And again, it rolls. I'll jump off to this briefly. It rolls right into sort of our umbrella host of Black Rock Observatory. Yay out there! Hi Zoom and others that are watching. I belong to Black Rock Observatory. I'm on the board of directors of the nonprofit. We take telescopes to locations where we're not expected to be. So out at Burning Man, we bring this great big 20-inch scope, big Dobsonian out there. We bring solar scopes. We have lecture space. We've had everybody from Alex Filipenko came and gave a lecture, which was kind of cool. Although he was stunned to find me, it was funny. I let him lecture. Then I walked up and I was like, "Hey, Alex, what's up?" And he's like, "David, I didn't know you were here. Can we get a selfie?" It was really funny. But yeah, it was a good time. So anyway, we do cool stuff out at Burning Man, but also we're able to, I don't know if we ever do start making a little money through this webpage and get a Patreon, we're going to funnel the funds through Black Rock Observatory because it's an official nonprofit. And then we can use those funds in a nonprofit way to bring education for science and astronomy while we're having a little fun doing it too. So that's our ultimate goal. And we want to make this a travel show eventually. And that's kind of the first topic I wanted to bring up tonight is where are we going to go? Where should we go? I know nobody's watching on YouTube, so turning to our audience.
There's 9 whole people
Just
watching.
kidding. We got 10 now.
Do we have 10 now? So well, the question is, are they watching from back at the beginning, or did they jump in at the live moment?
I think YouTube only lets you live.
Yeah, you can pause once you're in the stream, but you can only pick up the stream from where you start.
Well, welcome everybody. I'm sorry for the shenanigans with me giving you, I don't know, a false, I don't know, a bait and switch there. Really, I gave out a false link. Promoted.
Who do you think you are, Elon Musk?
Oh wow!
Oh ouch! Who would disparage Elon Musk?
Too soon. Not our Lord and Savior.
Sorry. So anyway, back to our point is where should we take this thing on the road? I mean, Griffith Observatory is going to be not Griffith, Mount Wilson Observatory. Griffith will be an obvious place to go eventually, but that has to be arranged and done in the right way. But Mount Wilson will be an obvious place to go. We have colleagues that work there. Amazing science was done at Mount Wilson. So beyond that, where should we go next? Where do you want to go?
What's wrong with a road trip where we take Vespas up to Keck? Totally affordable.
I'll have to learn how to ride a Vespa.
Me too.
What's the worst that could happen?
What could possibly
well,
go wrong?
with the protests, we might need to off-road them though. And I don't.
Okay, so we'll fit them with chunky tires.
Wait,
And-
we'd be
and
going up
honestly,
with
I
like
don't
little
know if
oxygen
I'm-
masks. Like,
I honestly don't know if I'm down with bypassing the protest, to be perfectly honest. Despite the fact that I'm overall pro TMT, I'm also willing to not build it on the island if that is what needs to happen in order to, one, repair the wrongs of the past that astronomy's done. TMT is doing amazing things, as our friend Mimi that joined us last week can attest to. She works up there at JCMT. She's a telescope systems scientist, and she does a lot of outreach, and she speaks with a lot of Native Hawaiians, and she understands what's happening, but is also very conflicted because this is another act of imperialism when it comes down to it. And I don't know. How does New Zealand feel about things like this? Do you struggle at all with, you know?
No.
Just no.
Sorry, everyone's been really good. We've had like a few hundred like warnings and like maybe a dozen arrests. I don't know exactly the numbers, but we're pretty good here. Like we look at America and we're like, oh my God, are you okay? Are you okay?
oh no, not for the.
Oh no, but that's just. I was talking about the protests of the protesting of TMT on Hawaii.
Oh shit! I had protests and I was like protest of COVID-19.
No, but you're very justified in saying that. No, we've got a lot of crazy people here.
So here's the thing.
California, the people, there's some folks in Huntington Beach, just 45 minutes from here, half hour from here. Yeah, they were protesting. I don't know. They're nuts. I don't know.
Okay. Ventilators up, bro.
That's why I've turned to whiskey, everybody.
What are you protesting? What do you got?
I'm on.
Oh, and by the way, Huntington Beach brings us tonight's Basil Hayden. H is for Basil Hayden. And it's the whiskey I'm drinking tonight. If anybody wants to sponsor a whiskey or has one we should try, let us know. You can send us an email, leave us a comment, follow us on the Twitter, although none of us are running our Twitter page. Boodles Gin.
I need more Boodles, London. Send for Boodles.
Boodles and boodles of it.
See, I love how I'm just alluding to. I like how I allude to give us free booze, and Jared just begs. It's.
You know, sometimes the straightforward method is just better, more efficient.
No one's ever gonna say I wasn't honest.
And
but you need
I
to
look for
respect
any
people
excuse. I was gonna say because I look for any excuse to do an accent. Irish mist. It's Irish whiskey imbued with honey.
Anyway, back to our serious topic. See how serious we can get here for a second. The protests of TMT, and we had a friend that joined us last show, who's a telescope systems scientist up at the James Clerk Maxwell Telescope up on Mauna Kea, and she does a lot of outreach, talks to the Native Hawaiian population, but at the same time is very conflicted because she sees both sides of it, but also understands that these are opportunities that don't exist otherwise, and a lot of the folks that live there are pro that. And the media picks up on The Rock going out there and saying, you shouldn't be for this, it's terrible, they're going to pollute the water. Well, there's no water up there. There's no water.
Oh, yeah, it was Momoa.
It's
it was
not
Momoa
about,
that did that, but The Rock also was protesting.
It's not about the water, though. It's about the cultural aspect of Mauna Kea.
Yeah.
Exactly.
How important it is culturally. And
yes.
how little Europeans have respected that.
Yes.
And so if there hadn't been so much disrespect from the Europeans, like historically, of this place, then it probably would be a different story today. But we can't just ignore the fact that historically there has been a lot of disrespect from the European astronomer community and American. Like Americans are not Europeans, but you know, a European
Pretty
descent,
much.
not Pacifica. And like you've seen those emails that have been passed around the astronomy community where people are like, oh, a herd of locals or whatever, like really dehumanizing names used for these people fighting for their mountain. And in the Pacifica culture, mountains are really, 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 really important. It's difficult to understand from a European standpoint, but it is very important in a lot of cultures of the Pacific. And we can't ignore that. Yes, it's a great opportunity. It's a great mountain, but La Palma is a great mountain and it's in Europe. And it is possible, and I'm starting to get to like be comfortable with the fact that it's possible we blew it. It's possible our community just blew it with the TMT, and this is a trust relationship that can't be repaired quickly enough. to allow that kind of stuff to go forward the way we want it to.
Yeah.
But there's a point where we're going to have to cut our losses and be like, we screwed up. We need to apologize really bad and show goodwill and show that, you know, we want to respect these communities. We want to come at it from a place of understanding and like.
See, but that's just it. That's just it. That's just it. Is TMT actually has been doing that, and that word is not getting out. They have held multiple over and over again. They're holding.
Doing that recently, just because it's been doing that recently.
No, they've been doing it for many years. It's been going on for many years. No, many years. You go back and back and back. There's community meetings. There's more community meetings. There's more now. That is not to say I don't agree with your point, because I still say if we need to not build it there to move on and to repair the wrongs of the past, I'm willing to do that. Yeah, but we need to admit that's why we're doing it.
About the herd of natives, they were recent. It was the 2000s. It was.
Oh yeah. No.
It was not 100 years ago. So this is trust that has been lost recently. And yes, good people with good intentions are probably doing their best, but unfortunately, they can't erase the mistrust of the past.
Yeah, that's, you nailed it. Yes, thank you. You actually spelled that out better than I've been able to. It's
enormous drink.
Well, it is, but I've turned towards the notion of this doesn't make a lot of sense to understanding. It doesn't need to make sense to us because it's not my culture. It's not my viewpoint. Doesn't come from me. And we can't be imperialistic about things just because we want to go do some science.
Saying it doesn't matter just because it doesn't matter to you is neocolonialism. And white people need to seriously get off their high horse about that. Like, it's basic human empathy.
Yeah. Right.
Yet at the same time, our friend that works up there and interacts with the folks that live there, now she admits she does have a bias towards people that speak to her tend to be more excited about science because she's doing science fairs, she's doing outreach to kids. So she's getting that viewpoint. But she does say there's a significant fraction of natives that are actually a little bit afraid to speak up and say, well, I wish we could come to an agreement on this in certain ways. And it might not be able to happen only because of the horrible behavior of the past of Keck, of Subaru, of the other scopes up there where, yeah, they had all these promises and then they didn't follow through. And if that's the track record of big telescopes up there, what do you think people are going to do? What do you think folks that, you know, you're not going to believe TMT, even if TMT is coming through now, you know, it doesn't matter. They'll say it's all until you build it and then you're going to shut it down. So I don't know. We'll wait and see. But La Palma's not a bad site, but at this point, TMT would no longer be first, even going to La Palma. A few years ago, if they had switched right then, they would have been on Sky before, you know, the ELT. But
one last question on this, because I haven't been following the negotiations too closely, but have they offered to kind of relinquish power, get the telescopes built by letting University of Hawaii take the lead?
That won't be good enough. University of Hawaii, like any university, is bringing in students from wherever, so it's not a direct channel in. TMT has made promises of hiring
I know about the builders
and the school. They've done a lot of things, but again, it's not about money. It's not about offering. That's all happened. It's about the fact that essentially it comes down to the fact that Hawaii was taken by the Marine Corps and plantation owners of you know, pineapples and created a state by white people. So, you know, this is a fight about sovereignty, and TMT has become part of that. It's you know, it's not about science. It is about the mountain, absolutely, but it's really about sovereignty and them just wanting to have the say. If they had the sovereignty, they might even say, sure, come build it on our island under those same conditions because we're the ones that are getting to say, yes, we run the island.
That's what I'm saying.
That's not going to happen in the next times. I don't know. I kind of think TMT should move on, frankly. Hey, Mike Bolte, are you still one of the TMT folks? Move on.
Yeah, and it's really
moving on.
I was going to say it's important too to realize that TMT isn't the only part of the sovereignty movement on Hawaii as well. So it's just but it's one of the more sort of, you know, out in front of people.
It gets more international, interstate publicity. Yeah, definitely, because it's an interstate, international project.
Yeah. So I want to turn to our next subject, which is, and Jeff, we might not even get to your what funds a NASA or what funds a NASA project, because we've had too much fun getting political tonight. But Sarah, behind you, you have a Hubble Space Telescope image.
I do?
You do. You got the horse head picture it took.
Do. I love this picture. It's not my favorite Hubble picture, but it's a good one. It's got texture.
It does.
And it's its 23rd anniversary, 23rd birthday infrared image. That's right. Hubble does more than visible light, y'all.
Well, what did it take it with? Which camera took that?
I don't know. The infrared.
You're no help. What year did you say that was the 20? What year anniversary?
It's the 23rd anniversary.
Oh, it was with C3 then, I'm sure.
Yeah.
Must have been with C3.
Of course.
I would guess.
But let me see.
But anyway, so Jared, you and I were having a conversation one day about ways we could maybe make some money for this crazy show, so we could fund our adventures places. I don't know if anybody ever typed in anywhere we should go. We asked for places. Yeah. No, they're just
April. April did. No.
April did?
Okay. So April said we should go outside to our backyards and look at the moon because no one can go fucking anywhere.
That's a fine idea, April. And
I paraphrased, not as cursing.
That's fair.
Well, I was going to set up a telescope tonight. Use some of our imaging software that's been gifted to us. And anyway, it just didn't happen. So that's not happening this time. But maybe next show we'll show some live shots of the moon or something if it's out there. But we need money to take this thing on the road. It's going to cost a little bit of money. Nobody can fund that sort of nonsense. So we thought, well, let's sell T-shirts. And where can we get some things to put on T-shirts? NASA. NASA gifts all the Hubble images to the public. They're all public domain. That's why you see them on T-shirts and you see them on leggings and you see them on. Okay, maybe it's only astronomers that see them all these places.
And don't forget. The European Space Agency, ESA, is also a part of the Hubble project as well. And I really got to give props to ESA because this is like one of the few missions where they actually release the data to the public. Most of the time, ESA is just like, nope, it's ours.
But we've decided we're going to start letting you folks vote on which image we should stick on a T-shirt. And then we're going to let you buy it. So.
All right. So each of us has picked our favorite Hubble image, and then everybody's going to vote in the chat. And then that image, whatever is everybody's favorite, will go on a T-shirt with maybe some funny Space Force 5000, Space Force Theater 5000 slogans.
Yeah.
We have very strong brand identity.
I feel like it should say no royalties to NASA or something like that on it.
Well, it might talk about how much money we've made on it. We might make different runs of the shirt that let you know your T-shirt made this much of a total we've made and how much the instrument cost NASA.
Thank you. Thank you for the $2.13.
All right. So for
with C3, it was launched on shuttle mission whatever, which cost this many million to get to orbit. Speaking of Hubble, there it is.
Right. So I did, as I was looking for Hubble images for the 30th birthday, happy birthday, Hubble. It's a couple days late, but that's okay. You don't notice. So I found this image. I love this image. But the first thing that came up was this one. Somebody has, they slightly adjusted, they color corrected it a little bit up the contrast. And then they watermarked the shit out of it and claimed it as their own. You need to pay this stock photo company to use a NASA image that we, the American public, paid for.
Wait, Doc, didn't they do that to your face once?
Did they? When?
I think they did. I think there is a photo of your face on Alamy that just has their watermark all over it.
If you can find that, that'd be amazing.
Let's see if I can find it.
How is that legal? How can they take people's pictures and
America?
Disney has fucked our copyright law so much. I'm sorry for swearing.
Just wait till you find out what we're gonna do with all this footage we have of you tonight.
Wow, it's gonna be interesting.
All right, here it is. I found it. Go ahead and screen share over to me. How do I do that?
Screen share.
There we go. Got it. And there it is.
Yeah.
Yeah, that is from probably 2000. Didn't we have a partial polar eclipse?
Yeah.
Was that the annular one? I went to Reno for that, so I saw.
You should ask them for royalties. You should be like 50% of of
I
revenue
should.
that is yours.
Let's sue him on behalf of Black Rock Observatory.
Let's do it. There we go. Our first major lawsuit. What a milestone.
Right?
Wow.
Oh, I look so terrible in the photo too. Thanks, guys. For making that.
You're welcome. I'm gonna put this as my
not you.
Zoom
I'm talking about
background.
Alamy. No, it's not that bad.
Yeah, save that.
You were watching you save to your desktop.
I'm kidding.
Wow, so I could show up in all sorts of nonsense now because people will go buy that and throw it in their magazine.
Yeah.
That doesn't
Absolutely.
seem legal. How
That's
do I
amazing.
have the right to do that? I feel a little, ever so slightly violated, but on the other hand, as a white male, I probably deserve it somehow.
Let's see. Let's see.
Screen sharing.
Let's see. Personal use. Oh, it's only $20.
You can
Maybe I
buy
should
your
buy
own
my own
thing
photo.
for
Oh, but if you want to
$20.
use it for magazines and books, it's a whole $69. Nice.
Oh,
Nice.
69, dude.
99. So
Ah.
now if I buy it a whole bunch of times, will it up my value, do you think?
Ooh, maybe.
I don't know if that makes sense. Now, can we get back to the point here? Can we look at our Hubble images? That was a really enjoyable segment there, I'm sure, for all of you out there to laugh at old Reitzel.
All right, I'll go with my favorite Hubble image.
All right, what do you got?
I got, one second, burp, 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 sharing my screen with y'all's, and oh, I have to get it. There we go. I had to go old school.
Old school
1995 Eagle Nebula.
creation there you got.
Yep.
Classic.
I remember when I was a kid and we got our first computer and we had to like swap the phone cable out to plug the modem in, and I watched this fucking image build line by line as I was downloading it. So I've got fond memories.
All right, so that's an image that we will put up there for folks to vote on that we can throw on a t-shirt. So Jeff, do you have one for us? All right, Jared, do you have one ready for us? He's gone mute. But
Oh,
I
wicked.
sure do have one ready. I hope you all are ready for this.
all right,
Oh,
let's
yeah.
see it here. Let's see it.
All right, here we go. Let me know if you can see it.
No,
beautiful.
drum roll.
Wow.
Is it behind
Ah.
you? Is it
Awe-inspiring.
Hubble behind you?
Bigfoot go.
Are you being funny?
Okay, here we go. It
It's-
should be sharing now.
No.
Oh,
There
there
we
it is.
go.
There it is.
There we go.
Oh my God, I'm waiting. This is so
It's
exciting.
Also, it's
Ah! Yes!
Creation. Team
Yep.
Eagle Nebula.
but of course, just
Image.
like Sarah, the 1995 version of it, the OG.
Yes. 'Cause
You don't want the one that we took with
Eagle
the advanced
Nebula.
camera with for
Um,
surveys or the WIPC 3.
No.
No.
It's like
Yeah.
CGI. It's like CGI versus practical effect.
No,
You
the
know, like
reboot's
practical
almost
just
never
looks
better.
better.
Absolutely. This is
Um,
absolutely Stan Winston.
I always remember this simply because when I was a kid and I visited Griffith Observatory, seeing the planetarium show where they did a daily one where they said, "Here's what's up in the sky." They had a whole round of like, "Here's some cool photos that Hubble just downlinked and we're now all looking at." And this was one of them that they showed on the big dome in the planetarium. And there's like a little filament of gas up near the top of the
Mhm.
really high pillar there.
But they
And
nicknamed, you gave it a name.
no, I didn't give it a name.
Okay.
But whoever was the lecturer that day used their little pointer and they said, "That right there is about the size of our solar system." And when 6-year-old me just lost, it's like I just hyperspaced through everything at the realization of that, like that. I feel like that really set everything off for it.
Okay. That was heartfelt, Jared.
Mm-hmm. That's what's up.
No, but that's actually a great story. All right, so we have Eagle Nebula. Jeff?
Anyways, yeah, I picked this one
Ooh.
because it looked nice.
All right.
All right, what's going on there? I think I know, but
It's HH23. It's some kind of jets.
H.H. Herbig Haro object, and you know the story.
Yes.
Was it Harrow that worked at the observatory?
He did. He was a guide.
Oh, really?
Yeah, the same job as you three up at Griffith Observatory. He used to go up to the telescope at night, would take observations, and he's credited with naming these objects. There's stars that are forming that have jets that shoot out of them. And we think the mechanism is probably similar to the jets that form in neutron stars, quasars, magnetars, AGN. There's jets that form all over the place, but this is one of the smaller objects that'll actually make a jet as it's doing something. So they're super cool. It's a good choice.
I just thought it looked cool.
It might look good on a t-shirt, maybe on a brown t-shirt.
Yeah.
I don't know. Well, I'm going to go second to last, and we'll let our guest give her choice for a Hubble image, and then we'll let her take over the show. My choice, let me share the screen here, is one of my favorite galaxies. And here we go.
Sombrero!
That would have been my second choice.
Yeah, I love the old Sombrero galaxy. It's just so weird looking. It's, you got the almost quintessential elliptical galaxy there in the middle of it. Picture the big fuzz there, everybody. You got an elliptical galaxy. It's even elliptical, but on top of it, you got this amazing disk of dust and gas, and it's really cool. I couldn't throw in the image where there's a Spitzer one they've added onto this. Took some infrared images that shows the dust lanes. They really stick out. Couldn't pick that out because this is for Hubble 30. Happy birthday, Hubble. So if you like this one, you're going to be able to vote for it. We're going to make a Google form. We'll tweet about it from our Twitter account, and we'll also each tweet from it. I'll tweet from it. We'll put it on our YouTube, and then you'll be able to vote. We'll leave it open until the next show or two. I don't know. We'll do this every once in a while, and then we'll make some t-shirts. You think we got this thing thought out? It's only sort of. But anyway, I want to turn it over to our guest. But first off, what's your Hubble image? This is Dr. Eloise Savants, who's honored us with her presence tonight. She didn't know what sort of shenanigans she was getting into. But I hear you brought a Hubble image for us.
I did, and actually it's a Hubble image that you will see in my presentation. You can see if you can spot it. So let me try and get that share working. Can you see this?
Oh, yeah.
Crab!
We like it, the crab.
Love it.
I love the crab. The Crab Nebula is awesome for so many reasons. So that is a supernova remnant. So a massive star that exploded, and you can see it's really asymmetric, which speaks to me on a very special level because asymmetry of core collapse supernova was like my topic in my PhD. And so the blue glow is electrons that are spinning around at nearly the speed of light and creating light. And if you Google the Crab Nebula, this is a Hubble special, so I only took the Hubble image, but if you Google the Crab Nebula, in 2017, they put together a new image that includes Chandra images, and in the center, you can see the disk around the neutron star in the middle, and it is out of this world. It looks like CGI, but it isn't. It's crazy.
Yeah.
And the crab is so bright in the X-ray. One of my colleagues who's been doing X-rays for many, many, many decades, told me that people used to use the crab as its own unit. So like an X-ray source would be like a millicrab, because the crab was the loudest object in the X-ray.
It's adorable.
Which is a millicrab. I love it. Anyway, so that's my pick.
That is super, super fun. I have memories of a professor of mine at Lick Observatory, UC Santa Cruz, where I got my PhD, Bert Jones, where he would talk about how they went and got images of the pulsar the first time, and forgetting whether it was him that got it. I should have done this research ahead of time had I known you had that, but they actually built a mechanism that would spin to eclipse the light coming in, and they could time the pulses with the spinning to be able to turn on and off the pulsar down to the center, so they could get an image that didn't have the pulsar and an image that does. So maybe I'll show you that in the next show if I remember. Probably not. You folks can Google it, but it's just super cool how astronomers get creative to find that stuff. But that image of the Crab Nebula is amazing, and it ties into your topic tonight about exploding stars. So I'm going to, since I'm the one streaming, I'm going to pin you, and that should hide all the rest of us. So let you take it away. You should be able to share your screen if you like to. And afterwards, we will get to some questions and have some fun. So take it away.
Awesome, thank you so much. So I'm going to be sharing my screen because I've got a few slides to help assist me in this presentation. Can you see everything?
Sure can.
I can see everything.
I love it. In the background is one of my favorite pictures, but it's not just Hubble, so I couldn't use it today. It's Cassiopeia A, and again, you'll see that pop up during the talk. So this is really a topic that I find so interesting, and it's my favorite in all of astronomy. It's how stars die, and really violent and destructive deaths that also create the building blocks of life on Earth. Like our Lord and Savior said, we are made of star stuff. And he was right. You know, all that stuff comes from supernovae and their progenitors and what comes after them. The oxygen in your bones, the calcium, the oxygen in your lungs, the calcium in your bones, the iron in your blood, all of that stuff comes from supernovae, whether they are exploding massive stars or exploding white dwarfs. Even the stuff in our technology, like aluminium, not aluminum, aluminium, silicon, copper, comes from these explosions. And if you're looking at something a little rarer, something a little more exotic, like palladium, silver, platinum, or gold, if you're fancy, then you're going to need a rarer explosion merging neutron stars, which we call kilonovae. Now, I'm going to focus on supernovae, but we're going to talk about our kilonovae at the end of the talk, and we're even going to dabble in the little history of novae as well. So let's dive in, but before I tell you how they explode, I need to make sure we've got the basics. What's a star? Okay, for all intents and purposes, this will be our star today because I didn't feel particularly creative. And if you ask someone what a star is, they'll be able to tell you that it's a big ball of fire, a big ball of gas, a big ball of plasma. It's mostly made of hydrogen to about 3/4. About a quarter is made of helium. There's trace elements of other things like carbon, calcium, all of that. But what's very important with our star is that it's really massive. And so it's subject to an incredible pull by Lady Gravity. The sun is about 2 × 10⁻30 kilograms. So that's a 2 with 30 zeros afterwards. It's very difficult to picture how heavy such an object can exist. And if there was nothing to balance gravity, it would just collapse on itself. So we need something to balance gravity. And that thing is fusion in the core of the star. That fusion of lighter elements into heavier elements releases a tremendous amount of heat, which causes a lot of pressure inside the core that pushes outwards and stops everything from collapsing in and on itself. So a star, a very important element of a star that is alive, quote unquote, that's how astronomers think about it, is the balance between gravity and fusion in that star. And we'll see what kind of shenanigans happen when that balance is disturbed. So we're going to split our stars into low mass stars and high mass stars. That's just an astronomer thing. That's what we like to do because they have quite different lives. We classify them as less than 8 solar masses and more than 8 solar masses at birth. The reason we say at birth is because they tend to lose mass during their life, especially high mass stars. They can do that a lot. But their initial mass really dictates what kind of life they're going to have. So if we focus on our low mass stars, like we said earlier, there is this fusion in the core. And initially, low mass stars and high mass stars equally, they fuse hydrogen into helium. Hydrogen is the lightest element in the universe. And if you bang them together, you can create helium. And that releases a lot of energy. Actually, 90% of the life of our star is going to be spent doing that. But eventually, it is going to run out in the core. And when it runs out, it needs to find a new fuel to burn in order to balance gravity. And that new fuel is going to be helium. It's convenient. You've just made a lot of it by burning your hydrogen. It's the next element, the next lightest element. It just makes sense, right? When you burn your helium, you create carbon. In the process, you might even burn a little bit of carbon and create oxygen. You end up with a carbon-oxygen core. All is well until you run out of helium. Because low mass stars are not massive enough to burn anything beyond helium. It doesn't get hot enough. And so when your core is made entirely of carbon and oxygen, that's it for your core. Fusion just stops, it becomes inert. And so gravity wins because there's nothing to balance it. So it will contract and contract and contract. And that gravitational potential energy that is released is in the form of heat released into the envelope of the star. And that envelope gets blown away through interstellar space and creates a beautiful planetary nebula. So the orange bits in this picture are the remains of a star that used to be right there in the middle, but blew away because it reached the end of its life. And in the middle of that planetary nebula, you would find what we call a white dwarf. It's basically a dead star. That's the inert carbon-oxygen core of that star that's left in the middle. It's about the size of the Earth, but because gravity has pushed everything together very, very close, you can pack half the mass of the sun in this tiny, tiny space. The Earth, for comparison, is about 100th of the radius of the sun. So the volume is an absolute fraction of that of the sun. And you're packing about 0.6 times the mass of the sun in there on average, but you can get all the way up to 1.4 times the mass of the sun in a white dwarf. Really crazy. And something very important to note, which I'll get back to in a minute, is that because gravity has pushed everything together as tightly as it can be, it's turned into a new state of matter that we call degenerate. So we know of a few states of matter. We've got solids, we've got liquid, we've got gases, we've got plasmas, which is gases where the electrons have been pulled off the atoms. And then when you can add degenerate to that list, but it's very special. So our white dwarf, if it's on its own, will not do much. It will just cool down until the heat death of the universe. But if you add to it a companion, very interesting things can happen. If that companion gets too close or bloats too much as it ages, then material can be stripped away from the companion and accreted onto the white dwarf. Now, if that white dwarf gets too heavy, that material around it will ignite. But because the densities are so high, that material, as well as the white dwarf, is also degenerate. So what does that mean and why is it important? Well, degenerate matter, when temperature increases, pressure will not increase. Now, that might sound like a bunch of physics mumbo jumbo, but let me explain why that matters. If you've got a normal gas and you increase the temperature, pressure will increase, the gas will expand, and as it does, it will cool. Therefore, it's a self-preserving system. You heat it up, it expands, it cools, it balances things out. If it can't expand, then temperature is stuck inside of that material. Now, if that material is hot enough, fusion will start. Energy will be released. The temperature will rise, but the heat has nowhere to go. So fusion will happen faster because the temperature is higher. So more energy will be released, the temperature will keep rising, and fusion will happen faster and faster and faster. That's called a thermonuclear runaway. And that can turn your white dwarf into a supernova very quickly if that white dwarf is massive enough. And if you wait just a few hundred years, you get beautiful supernova remnants like Tycho's supernova or Kepler's supernova. And you can see how beautiful and round they are. That's kind of a feature of thermonuclear supernovae. Their explosions are quite spherical, although not completely. They leave no remnant behind. The white dwarf is completely decimated. It's completely burnt to a crisp. Everything's burnt to basically iron and nickels levels. And that's where most of the iron of the universe comes from. Now, if we look at our high mass stars, things are going to be a little different. At the beginning, pretty much the same. You burn your hydrogen. You run out, you burn your helium, and then when you run out, you can start burning carbon, and then oxygen, etc., etc., etc. Our high mass stars are massive enough, are hot enough in the center to do that. The problem is going to happen when your core is entirely made of iron, because iron is not a fuel. You can't use iron to release any energy in any way, shape, or form. If you bang two nuclei of iron together to create something that is heavier, it's not going to release energy, it's going to take it away from the system. This means that there is nothing to balance gravity anymore. and so the core will collapse. In a quarter of a second, the equivalent of 1.5 times the mass of the sun is going to condense into an object that's about the size of a city. And I'm European, so we have pretty small cities, about 20 kilometers across, something like that. The pressure and the densities are so high that protons and electrons are going to be forced together to create neutrons. And you're going to get yourself a neutron star with the density of an atomic nuclei. It's very difficult to picture how dense that is, but I've got a little analogy that might help. If you just took one of your red blood cells, tiny cells, and they had the same density as a neutron star, they would weigh the equivalent of Donald Trump. And you've got to admit that's pretty dense. Now, the rest of the envelope of the star is also going to collapse, but a bit slower, and eventually it's going to encounter that neutron star and bounce off of it and launch a big shockwave through the star that explodes it into a supernova. And then a few hundred years later, you get Cassiopeia A and the Crab Nebula, my favorites. As you can see, they're not nearly as round as the thermonuclear supernovae I was showing you earlier. They're very, very messy. And that's not an effect from the interstellar medium that they evolve in. That's because the explosion mechanism itself is really, really messy, and you can actually measure this. Now, let's recap very briefly. Our thermonuclear supernovae from the low mass stars leave no remnants and make most of the iron in the universe. Our core collapse supernovae, they make neutron stars or pulsars, which are basically neutron stars on crack, or they make magnetars, which are neutron stars on double crack. They can also make black holes, and they make most of the intermediate mass elements, well, a lot of the intermediate mass elements like oxygen and all of that. But what's so cool about these supernovae? Well, the fact that they make the building blocks of life is pretty awesome. But I'm just amazed at how powerful they are. They can release as much energy as the sun will in its entire lifetime. This ejector that you see, it is launched at incredible speeds of about 10,000 kilometers per second. That is not an upper limit. I wasn't being hyperbolic there. This is an average. This is a flimsy average. I have worked with supernovae that have ejector going at 30,000 kilometers per second. That's like a tenth of the speed of light. It's crazy. And a tiny amount of that energy is going to go into powering the light of the supernova that we actually see. And even that is enough for them to outshine their host galaxies sometimes. You can see 1994D here, which is a thermonuclear supernova, and you can see it's basically as bright as its galaxy. That's not an artist impression, that's a real picture. And so because they're so bright, you can see them from very, very far away from other galaxies. Most supernovae that we see are extragalactic because they're actually rare events. In the galaxy, in the Milky Way, so which is a pretty big galaxy, we expect about 2 supernovae per century. And even then, we expect that we can't see that many because even if they happen at that rate, we are within the Milky Way. And so if something happens on the other side, there is a lot of dust along the way that will block off that light. So really 99.9% of the supernovae we see are seen from very distant galaxies. But what's next? For our thermonuclear supernovae, nothing, because there's nothing left. There's no remnant. For our core collapse supernovae, however, we have neutron stars. And these neutron stars can do crazy things given the right conditions. If they're in a binary system, which is very likely, especially at birth, most massive stars are in multiple systems, binaries, triples, quadruples even. So if they're in a binary system and both stars go supernova and leave behind a neutron star without disrupting the system entirely, because they're very powerful, they could easily do that. And if these 2 neutron stars are close enough together to merge within the lifetime of the universe, then you can get yourself a neutron star merger and a kilonova. Now, you might have heard about neutron star mergers with respect to LIGO and gravitational waves. And that's because, you know, it's a very important part of this process, because without the gravitational waves, you don't get a neutron star merger. It's the energy that is released in these gravitational waves that shrinks the orbit between the two stars, because energy has to come from somewhere. But as the stars are drawn together, the amplitude and the frequency of these gravitational waves also increases, which means that they need more energy, which means that they carry more energy away from the system. And this is a self-feeding cycle. Eventually, your neutron stars will merge, right? And when that happens, a whole series of events occur. Your gravitational waves, which we have talked about. This is, by the way, just an artist impression. Don't pay no mind to the actual shape of it. And short gamma ray bursts, SGRBs. Now, we've known about short gamma ray bursts for a long time. We've been observing them for decades. We were pretty sure they were from neutron star mergers, but we weren't sure until we observed both a gravitational wave and short gamma ray burst together, which we did in 2017. So now we know this is where they come from. A short gamma ray burst is launched a few seconds, like 1.5 seconds, 2 seconds after the merger. So as they come together, because you end up disrupting one of the stars, one of the neutron stars. So it forms a little accretion disk around one of them. And then this material is accreted onto the bigger neutron star. This accretion disk can launch jets. So we were talking about jets earlier. Jet formation is practically the same across the entire universe. You've got an accretion disk. This collimates your light, because gamma rays is just light. They're just the most energetic photons in the universe, but it's still in the electromagnetic spectrum. And so you get this very narrow beam of light launched through space. They are called short gamma ray bursts because they last less than 2 seconds. And that's not all, because what we can actually see with our optical telescopes is not the gamma ray burst, not the gravitational waves, it's the kilonova, it's the ejector in that merger that glows. Because that merger is not clean at all. It's very messy. You disrupt one of the stars, things get scattered everywhere. And it's a prime location for the R process, which is a type of nucleosynthesis where new elements are created. In the R process, which stands rightfully for rapid process, you get an atomic nuclei, say iron. And you throw a bunch of neutrons at it very, very quickly. So quickly that nuclear decay does not have time to happen before you fill it with neutrons. And you can create very heavy nuclei like platinum, gold, silver, rare earth elements, all of that. Now, nuclear decay will happen, definitely, and rather quickly. And that's why this stuff glows, because it's very radioactive and it sends light across space. And you can see it glowing for days. This is an example of a kilonova. Actually, the first and only neutron star merger that we've observed in optical light. That's 2017 GFO, which I cannot help but read 2017, get the fuck out. I'm sorry, I can't. It always goes like that in my head. And this is the counterpart to the first neutron star merger that LIGO, Virgo, etc. observed in 2017, GW170817. And you can see in this little GIF how the light on the 22nd really fades away very quickly. And you can see the light curve here. It's a very rapid decay, but a similar shape to supernovae, if you know what a supernova light curve looks like. So I think that's enough physics for the day, and I'm going to wrap up very soon. But first, I think I want to address a question that I very often get. It's why all of these nova, supernova, kilonova terms? Where does that all come from? Because they're quite different objects. Where does that come from? Sorry, I needed a drink. And the answer is history. Like most observational taxonomies, it's a little bit of a mess, but it sort of makes sense if you know the history of it. Now, we'll get back to that picture because this picture is a lie. I used it to talk about thermonuclear supernovae, but that's not what this image was made for. It is actually a picture of a cataclysmic variable. I'm not going to go into the details, but these are the systems that lead to novae, the classical novae, where a white dwarf gets material from a companion. The thing is, the system is very much the same for a thermonuclear supernova. It's just a little more extreme. In a nova, only the outer layer of the white dwarf, I mean, the material that's been accreted on the white dwarf, will burn, will ignite, and explode. So you still get an explosion. It's not nearly as bright as a supernova. And it doesn't disrupt the white dwarf entirely, and it doesn't make the same elements, but it's a very similar principle. Now, people knew about novae and like new stars that popped up in the night sky for a long time before they knew about supernovae. It's just that in the early 20th century, they started realizing that there were other galaxies, and some of these new stars came from much further distances away. And so they were much, much brighter than the classical novae that they knew. And since they were super bright, they call them supernovae. I'm not kidding. That's just where it comes from. In fact, supernova used to be hyphenated. It's just that over time we lost the hyphen, but that's where it comes from. And as for kilonovae, some people a while ago were theorists were trying to calculate how much energy would be released in a neutron star merger. And they got to a number that was about 1,000 times as much energy as in a nova. And 1,000 kilo nova, like a kilogram is 1,000 grams. That's it. I don't even know if that number is even accurate anymore, but we're kind of stuck with this notation, so it's better not to think too much about it. So anyway, I'm going to leave it at that for now. And if you've got any questions about any of this or anything else, I would love to answer them.
Awesome. We actually do have we have a question from the YouTube chats.
Do we have some questions from the YouTube chats?
We do.
If you could unshare your screen, and then we will all be able to join you in here. Awesome. And we'll go gallery view. That was a fantastic presentation. First of all, thank you so much for bringing that to us tonight. I much appreciate that. And I want to point out, I got quite excited about you mentioning novae. I'm going to do the horrible thing that astronomers do all the time and point out something that I did, but I'm not on a whole lot of research papers, and I'm not on a whole lot of nature papers, to say the least. And this is actually a nature paper that I'm on. I'm on a couple of them, but an ancient nova shell around the dwarf novae, Z Camelopardalis.
Oh yeah, nova shells.
Yes, nova shells. So I took some of this data and it ended up in a nature paper. So I'm on this nature paper. It was pretty cool. So I'm very proud of that paper, and novas are cool. So thank you for talking about them. Yeah, it's always exciting. You periodically you'll hear about a new star in the sky, and you can go look at it and be like, what? Why did that? Where'd that come from? It's not just to be there. So that's pretty cool. Now, what's the question from the YouTubes? And
all right. Let me see. I think it was Alan who was asking. Yes. Okay. So these events, they're really fast, and his question is, I think, about core collapse. So if it happened, if they were balanced to begin with, why is there such asymmetry after the explosion?
So it's because of the way that core collapse happens. It's not necessarily it's not a symmetric explosion. There might be sloshing around because things don't fall particularly evenly. Everything is messed up inside. Because like the collapse doesn't necessarily start from the exact middle, and so there are acoustic waves potentially. There's there might be jets if you've got a black hole that forms in there, and so there are a lot of reasons why this might get really messy. Yeah,
there's some fantastic simulations that you can take a look at if you Google simulation. You know, some of these things.
Yeah.
I saw an interesting result, gosh, it was just a couple of days ago, that they finally have found a galactic source for a fast radio burst. And it actually was a magnetar. So it was an eruption on a magnetar, probably some sort of magnetic realignment, but it would have been detectable at extragalactic scales. So what am I saying, folks? Out there are these weird radio bursts, very short, lots of energy, but in the radio part of the spectrum. So kind of like the gamma ray burst that lasts a couple of seconds and go away, except gamma rays are really high energy photons. These are radio blasts, still a lot of energy in them because you're seeing them from large distances across the universe. We didn't know what made them. We weren't really sure where they were coming from. So there's a couple of them that repeat that we're able to study and slowly learn about, but finally our first one from our own galaxy, and they were able to pinpoint it from a highly magnetized neutron star that is actually a product for one of these explosions you were talking about. So I did tie it all the way back around. I was
Yes.
folks. So what makes a magnetar? How do you end up with a magnetar instead of just a neutron star?
Yes.
And do colliding white dwarfs ever make a neutron star, or do they just always blow themselves up as well? Because I know some type 1a supernovae are actually colliding white dwarfs. They're not all.
Yeah. So there are two main schools of thoughts for, and then there's this guy who comes up with his own theories at every conference. But there's two main.
Wait, who are you talking about?
No, Soka, it's fine. It's
no.
You don't know him? Yeah.
I've heard some stories.
He's always like, oh, I've got this paper accepted on archive, which is like, you just put your own stuff on there. It's like, it's very funny. He gets arsy if you don't mention his theories. Anyway, it's not my problem, not my field, not really. So there are two main schools of thoughts, which is what I explained with the accreting of the mass, or merging white dwarfs. Like if you've got white dwarfs in a binary and they merge. The essential part, really, is for a white dwarf to get too big. So to get above 1.44 times the mass of the sun, which is the Chandrasekhar mass, that's when they actually ignite fully and explode. Now, I'm not going to go into the details of the mechanism I've explained, the double detonation, which is very, very interesting, but not the point. I forgot, what was the point? Oh, yes, they don't make neutron stars. They just, because they ignite. And so, because to make a neutron star, you need that pressure to really put together 1.4 electrons and protons to make the neutrons. In a white dwarf, you don't get to that kind of level of pressure. You just ignite the entire thing and it blows up.
Yeah. So what causes the angular momentum to create a magnetar versus just a regular pulsar?
Because of the way it falls in on itself, if the star is rotating, and a lot of stars are rotating, and there might be stars that are rotating pretty fast, if the star's rotating, then it would already be rotating, but angular momentum conservation, if it is conserved or close to, then the smaller it is, the faster it's rotating, right? That's just how it works. And that's how you get a pulsar, because it's very, very, very magnetic. The exact details of magnetism inside of the way beyond me, the actual physics of it. But the essential part of it is you've got material that's very that's not neutral. You've got plasma essentially that's sloshing around. That's bound to create magnetic fields, and if it's rotating, then you can get those pulses for pulsars. Right.
So, but what makes one a magnetar? Is there a line they draw between it?
Yes, it's 10 to the 15 Gauss.
Okay.
10 to the 15 Gauss is a magnetar, and for context, 1 Gauss is about the equivalent of a fridge magnet and the magnetic field of the Earth. So
10 to the 15, 10 to the 12 is trillion, so we're 3 orders of magnitude higher than that.
Yeah,
so 1,000 trillion.
Yeah, it's pretty insane.
Yeah, those are good numbers. How's the YouTube stream doing? Any more questions from over there? They enjoyed your "Not My Problem, Not My Field." I like that.
Not my circus, not my clowns.
Not my circus, not my clowns.
Nice.
We did have a suggestion for a drinking game.
Well, we're already way ahead of the audience, right? That's for sure.
So every time you identify what the guest's field is, what their signature is, and then every time they say the core of their talk.
Oh, that could get dangerous. Well, we're getting near the end where we're going to wrap things up here. Although, like we always do, we're going to dangerously paste the link to our Zoom meeting into the YouTube chat, and then see who joins us in the Zoom chat. We'll shut the stream off. But if anybody wants to join us in the chat and say hello to our guests, who I'd like to thank one more time officially here. Thank you, Eloise, for joining us. Fantastic.
Thank you.
Like we like to think we're slowly raising the bar in the quality of our shows, and you took us a leap ahead, I have to say.
Oh, thank you.
My friend Mimi is fantastic. Just even having a guest last time was there, and now this time you came with a full presentation and all the rest, and I think yours was better because I didn't interrupt you like I did Mimi, frankly. So Mimi, you'll get another shot if you're out there listening. And but let's I don't know. Anybody have any final thoughts as I get the link here to paste into our chat?
Ooh, well, we did have a vote for best Hubble picture, and it was for the Horsehead Nebula from Deep Sky Dudes.
Expected result. Game's rigged
And
from the beginning.
David, one of our other coworkers, his vote was, we've got 3 for Pillars of Creation. So we're in the lead, y'all.
Well, like I said, we will make a Google form, and we'll insist you jump through a bunch of hoops. And we're not going to mail out ballots to everybody like California's going to do. We're going to make you prove ID. And
oh yeah, totally, absolutely. Oh, and I did have a thing for Hubble 30th. We didn't get to do the whole thing, but I had made up a thing. If you okay, so if you kind of look at Hubble as a person, I know you're not supposed to anthropomorphize space missions, but fuck that. I do anyway.
Hubble was another asshole, though.
Well, oh yeah, no, not him. But
not the man.
The telescope didn't do anything. Telescope didn't hurt nobody.
It's true.
So, Hubble, a functioning spacecraft at 30 years old, there are just 2 other spacecraft that are functioning older than Hubble.
Oh.
Voyagers 1 and 2.
Yep.
How fucking amazing is that? Right? Okay.
We're screwed when it's over, because Hubble is our last UV window on the universe.
I know.
So we're fucked when it's shut down, the UV window. So all the massive star stuff, we're like, yeah.
Is it too late to put a UV detector on W first? I know it's not anyway. The wide field wouldn't help us much.
We could ask the NRO about that. Maybe they can make it happen.
I think other people are thinking about UV missions to replace Hubble, but it needs to last until then.
Right?
Yeah, Mike, if you check this one out, my friend Mike Rich, a colleague of mine at UCLA, who was on the Galax team, maybe we can get some folks from Galax to come talk to us about what they're going to be doing to start getting more UV data, because Sky blocks it. Anyway, I'm going to paste in the link here, and then we're going to stop the stream. So, paste. There it is. All right, this gets dangerous now. Folks, 2 minutes here. Thank you all for joining us for our 2nd official episode of Space Force Theater 5000. And we hope it was fun. And we'll get back to you probably in a couple of weeks-ish. And then we're going to change it to a, I don't know, 2nd Thursday, third. I don't know. We got to figure it out, because our other show's every first Friday. And this happened one tomorrow night. I don't know. Maybe this was a good show, though. Maybe this works. Anyway, thanks, folks.
Thank you.
For joining us. Thank you, Eloise. It was wonderful.
Thank you.